used in the motor industry vary considerably from the thick lubricants used in the gearboxes of heavy plant equipment to the very thin oils found in delicate instruments. To identify one from the other, classifications based on the lubricant's viscosity or performance have been introduced by various bodies over many years. The purpose of this video program is to explain what the various classifications mean and how one classification relates to or differs from another. One of the earliest tests carried out on lubricants was to determine viscosity. Viscosity is the ability of a fluid to resist flow, or put more simply, a liquid's thickness or thinness. Thin fluids are regarded as light or of low viscosity, and thick oils as viscous or of high viscosity. It was the Society of Automotive Engineers who first classified oils into viscosity bands using a system of SAE numbers. SAE numbers are determined by a simple test which times the flow of a sample of oil through a viscometer U-tube. The tube is suspended in a viscometer bath, which is filled with liquid at a carefully controlled temperature of 40 or 100 degrees centigrade. It's normal laboratory practice to have several tubes in one bath. The flow of a specific volume of oil under gravity is then timed as it passes between two etched marks on the tube. This reading is used to perform a simple calculation to produce a viscosity rating for the oil in centistokes. This figure can then be related to a chart to determine the SAE band for that particular lubricant. The viscosity of a particular oil depends mainly on the base oils used in its formulation, or in the case of multigrades, the type and quantity of thickeners or polymers used in its production. As well as measuring the viscosity of an oil in a viscometer tube, it is also measured at various sub-zero temperatures in a cold crank simulator. This is to give an indication of the oil's suitability for use in winter conditions. Oils tested in this apparatus are rated with SAE numbers such as 0W, 5W, 10W, and so on. The W indicating the suitability of that oil for winter use. The cold crank simulator consists of a small refrigerator unit to cool the oil and a rotor turning in a cooled cylinder. The whole device is designed to simulate conditions similar to those found in an actual engine. The rig is instrumented to give readings of the rotational speed of the shaft, the temperature of the oil under test, and the current required to rotate the shaft. The readings taken from the gauges are then related to a calibration chart, from which the viscosity in centipoises can be read off. Centipoises, just like centistokes, can be cross-referred to SAE numbers simply by reference to a standard chart. In terms of engine lubricants, there are two types of oil, monogrades and multigrades. Monogrades are oils with viscosity quoted in just one band, such as SAE 30 or SAE 40. Multigrade oils, however, cover more than one SAE viscosity number. Their designation is made up of two viscosity ratings, one for sub-zero temperatures and the other for 100 degrees centigrade. This gives oil with SAE numbers such as 10 W40 or 15 W40. Another important term often used to describe an oil's viscosity characteristics is viscosity index, or VI. This is a measure of the effect of temperature on an oil's viscosity. Oils that thin dramatically on heating or thicken substantially on cooling are said to have a low viscosity index. On the other hand, oils with viscosity less sensitive to temperature variation are described as having a high VI. Multigrade engine oils have a high viscosity index. So far, we've looked at the way in which oils are classified by their viscosity. But viscosity alone doesn't denote the suitability of an oil for a particular purpose. For this, we need a measure of the way an oil performs and its quality as a lubricant. Specific areas of concern are its anti-wear properties, how clean it keeps the engine parts, its freedom from carbon sludge formation, its resistance to oxidation, that is, the resistance to form lacquers or sludge on engine components due to the effect of high temperatures, and its dispersancy, that is, the amount of control the oil has over the size of contaminants carried in the oil. Ideally, the contaminant particles should be small enough to flow harmlessly through filters, galleries, and the working clearances in the engine. The formation of small particles into large ones can result in clogged filters, premature wear, and blocked oilways. So, engine oils are classified by their performance or quality, as well as by viscosity. Here, there are various engine oil specifications and performance levels, based on the results of engine tests carried out on the oil. The quality requirements of an oil to suit a specific engine are usually quoted in the vehicle handbook. Unfortunately, there is no single international system for describing performance characteristics. As a result, there are several classification systems in current use. API specs, produced by the American Petroleum Institute. US military or MIL-L specs. European motor manufacturers' specifications, known originally by the initials CCMC, but more recently superseded by the initials ACEA, known as ACEA, standing for Association des Constructeurs Européens de l'Automobile, and specifications drawn up by individual motor manufacturers. Let's look at each system in more detail. The API classifications were drawn up by the American Petroleum Institute and fall into two categories covering either petrol or diesel engine oils. All specifications are prefixed by the letters API. The specific classification for petrol engine oils starts with the letter S for service. This is followed by another letter denoting the quality of the oil, A being the lowest. API SA, SB, SC and SD were suitable for cars of the 30s to the early 60s. With engine technology beginning to improve and power output increasing, API SE was introduced for cars of the late 60s to early 70s, followed by API SF for cars built in the 1980s. Problems of heavy black sludge deposits encountered towards the end of that decade brought about the introduction of API SG for 1989 and later models. Unlike previous changes, the move to SH in 1993 was prompted not by the need to solve engine problems, but to prevent unscrupulous oil companies making false product claims. Up to that time, an oil's API classification was determined by the oil company marketing the product. This system was open to abuse. If they wanted to, an oil company could claim that their product met, say, API SG by assuming that the good test results achieved by blending a particular combination of chemical additives with good quality base oil would directly relate to when they were blended with cheap, low-quality base oils. The SH classification has changed all that. Now, the oil classification decision rests with an independent body who require formal declarations to be made and kept of the precise formulation tested, including the base oils. This is because a change to a low-quality base oil can seriously influence all aspects of an oil's performance. The camshaft on the left is a good example of what can happen when a cheap base oil is used. Imagine what effect this scoring has had on performance and how much it will cost to put right. This is just one example. The same drop in performance will be seen in other areas, such as sludge formation, deposits, sticking rings, blocked filters, and so on. Most car owners' handbooks specify the required engine oil in terms of API classification, and manufacturers are now including the SH spec. All of the rigorous testing and physical requirements for API SH classification form the basis of the new SJ specification, which includes a requirement for demonstrating fuel economy benefits and, for some viscosity oils, limitation on the formulation. Turning our attention now to diesel engine oils, the American Petroleum Institute uses the same principle of classification for these oils as they do for petrol engine oils. But, in this case, the S for service is replaced by C for commercial vehicle. So, over the years, engine oils of API CA, CB, CC, and CD have been specified for various diesel engine trucks and off-highway equipment, depending on the age, severity of operating conditions, or power output of the engines. API CC is still specified for a number of lower-rated engines, with API CD featuring more as modern truck engines operate under increasingly severe conditions. API CE, CF, and CF4 are relatively modern specs and are for the oils used in more recently produced high-performance diesel engines. The second system for classifying oil performance and quality is the United States military, or MIL-L specifications. These are almost obsolete, but are still quoted in a number of vehicle handbooks. The third classification system was introduced by the European motor manufacturers in the form of CCMC specifications and is now obsolete, but still referred to in service literature and on oil containers. The specifications fell into three groups: CCMC G1 to G5 for petrol engines, the G standing for gasoline; CCMC D1 to D5 for diesel engines, and CCMC PD1 and PD2 specifically for passenger diesel cars. As with most specifications, they developed over the years as quality standards improved, finally becoming CCMC G4 and G5 for petrol engine oils. G4 describing SAE 15W multigrade oils such as 15W40 and 15W50, based on the results of tests carried out in European petrol engines. G5 applied to lighter viscosity multigrade oils such as 5W40 or 10W40. The G5 spec had a higher standard for shear stability. That's a measure of the loss of viscosity due to mechanical effects, such as where an engine oil is used in a gearbox. These oils must stay in their viscosity grades throughout their service life.
100, 45 right.
As oils of G5 classification were normally used in higher performance engines, greater importance was placed on the oil's viscosity at high temperatures and the control of evaporation. On the diesel side, CCMC-D4 was for most normal performance diesel engines used in road vehicles. CCMC-D5 was a high-quality oil aimed mainly at those higher-rated commercial vehicle diesel engines prone to problems of bore polishing. In the early 1990s, the CCMC organization ceased to exist, and a new European Motor Manufacturers Committee came into being, known as ACEA. ACEA stands for Association des Constructeurs Européens de l'Automobile. In 1996, new engine oil classifications were issued by ACEA, and these are gradually replacing CCMC classifications in service literature and on the oil containers of reputable oil companies. So what are these new ASEA classifications, and what do they mean to the motorist? The practical outcome of the new classifications is that the engine oils which meet them will be of higher quality compared with their former CCMC counterparts. Higher quality, that is, in terms of greater resistance to high temperature, engine wear, less low-temperature sludge, cleaner pistons, and fewer ring-sticking problems. Those are the benefits the petrol engine will see, while the diesel engine will see all of those plus improved dispersancy. How have these higher standards been achieved? The answer lies in the more severe program of engine tests which the oils have to pass before being given an ASEA classification, combined with some tight controls on some of the more critical physical properties of the oil. The engines used for testing oils in the CCMC program had become no longer appropriate to current engine designs, nor to current motoring conditions, while the engines used in the ASEA classifications are of current design and operate under conditions more related to today's road conditions. What do the new ASEA classifications look like, and what are the main differences between them? First of all, classifications for oils aimed at petrol engines are indicated by the letter A. This is then followed by number 1, 2, or 3, a number after the oblique in each case, indicating the year of issue of the specification, initially 96. Now, let's look at the individual classifications and see what they mean. Starting at the beginning, we have A1/96. Oils in this classification are aimed at giving maximum fuel economy benefits as opposed to maximum wear protection. As such, the vehicle handbook should be consulted to check that the manufacturer is satisfied that an A1/96 classification oil is compatible with that engine. Oils in this category will mostly be lower or thin viscosity oils. The next classification is A2/96 and represents the more conventional viscosity oils, such as the SAE 15W multigrades, although some 10W multigrades of the lower performance can also be A2/96. Cars running on this classification oil will mostly be of the family conventional performance type, operating with conventional oil change periods. Cars of the higher performance type and those whose manufacturers specify a longer oil change interval are catered for by the third ASEA classification, A3/96. Oils in this category will mostly be full, or at least part synthetic, to meet the stringent restrictions on evaporative loss and to stay in their original viscosity grade. They will also mostly be SAE 5W or 10W multigrades, though oils of other viscosities can be included provided they meet all of the requirements. So much for the oils for petrol engines. But what about those for diesels? The ASEA system for classifying oils for diesel passenger cars and light commercial vehicle engines follows closely the system just described for petrol engine oils. Naturally, the emphasis is on testing the oils in current engines, but there are also stringent tests to ensure the oil's ability to retain its viscosity or stay in grade and meet the evaporative loss requirements. As with petrol engine oils, there are 3 classifications which parallel the same letter, number, and year of issue system. For diesel engine oils, the letter B replaces the letter A. So, as we did before, we start with the classification B1/96 to describe those oils which give the maximum fuel economy benefits to those engines designed to accept oils which will be mostly of very low viscosity, as in A1/96. B2/96 classification oils are required to stay in their viscosity grades and cover a wide range of viscosities. Oils of this quality are aimed mainly at passenger cars and light commercial vehicles of medium performance. Catering for the higher performance diesel engines turbocharged or those working harder is the classification B3/96. This has stay-in grade requirements and a greater emphasis on the ability of the oil to handle heavier loadings of soot, thereby limiting the resulting thickening. Greater protection of the valve train is also required. There are also ASEA classifications to cover the heavy commercial vehicle engines, and these are E1/96, E2/96, E3/96, and E4/96. C and D have not been used to avoid possible confusion with other existing and obsolete specifications which combine those letters and numbers. While most of the E classifications are not applicable to passenger cars and light commercial vehicle diesel engines, it's worth mentioning briefly E2/96. This is aimed at engines designed to run with longer oil change intervals and performance maintained to meet emission requirements. As will be seen in the summary, ASEA E2/96 is met by Duckhams diesel. To make oils of the obsolete CCMC specifications meet the new ASEA specs is by no means a paperwork formality. It has been necessary to run each oil through the new program of engine tests and laboratory glassware tests. To pass these new and more severe requirements means that the oils need to have an estimated 20% increase in performance over that required to pass the previous CCMC tests. In addition to API, US military and European motor manufacturers' specifications for oil, there is a fourth group of specs released by individual vehicle manufacturers. These are usually designed to address specific problems which the manufacturer may have experienced. The target spec is then made available to lubricant producers to develop suitable oils. The principal motor manufacturers who have developed their own specifications are Mercedes-Benz, who have specs for every different type of lubricant; Volkswagen, who produce specifications for both petrol and diesel engine oils; BMW, who do the same; and the Rover Group, whose specs are known as RES and are based on the CCMC classifications. These Rover specifications are giving way to an approval system based on a register of oils meeting the various appropriate ASEA requirements. Porsche have a list of engine oils which shows the oils they have individually tested in their engines and approved for use in their cars. These oils need to be of ASEA A3 quality before being accepted for testing. Rolls-Royce have developed their own special valve train wear test, which oils must pass before gaining approval. Other manufacturers simply quote standard oil quality specifications, such as API, the US military, European CCMC classifications, or ASEA lubricants, as suitable for use in their vehicles. It is obvious from all this that Duckhams invest a lot of time and effort to ensure that their engine oil formulations are a careful balance of chemical additives and base oils to meet motor manufacturers' strict requirements of engine testing and physical properties. This is the reason that they, like all reputable oil companies, warn against the use of proprietary additives bought over the counter by the motorist. They can completely undo all of the care taken. Don't be taken in by the dramatic claims made by some companies in magazine adverts on the benefits of their products. A commonly used one is how cars have been driven round a racetrack with no oil in the sump and only the additive to protect the engine. Dramatic, but not a problem the everyday motorist is likely to have to take into consideration. Beware also of pseudo-scientific articles and glossy literature with views of the special additive under a microscope or colourful technical-looking charts. There are many different variations of so-called scientific tests, but few, if any, stand up to genuine statistical examination. Nor is any mention made of the undesirable side effects which frequently accompany the use of some additives. It's rather like thinking that using a special Grand Prix racing tyre on a standard family car would have benefits. It wouldn't, and it probably wouldn't even be legal for road use. But don't take our word about proprietary additives. You only have to look in the vehicle handbook. Motor manufacturers stress that the use of such products are at best merely an additional cost, but at worst can invalidate their warranty. In the past few minutes, we have tried to explain the quality and performance issues associated with today's automotive lubricants. It may sound complicated, but in the end, it's all about constantly improving quality standards. It will come as no surprise to learn that Duckhams have the very latest products to meet the very latest specifications. The 5-star range covers the lubricant requirements of every type of passenger car and light van and satisfies all the latest quality standards. QS is a full synthetic oil to the API SJ and CD CF specifications with a viscosity of SAE 5W40 and meeting ACS specifications A396 for petrol engines and B396 for diesel engines. QXR is a semi-synthetic oil, also meeting the API SJ and CD CF specs, but with a viscosity of SAE 10W40 and meeting ACS specifications A396 and B396. Hypergrade Plus is a new generation mineral oil meeting API SJ and CD CF with a viscosity of SAE 15W40 and ACS specifications A296 and B296. While Hypergrade is a traditional mineral oil satisfying API SG and SAE 15W50. And completing the range, Duckhams Diesel, the most advanced diesel lubricant, which meets the API CD, CE, CF4 and SG specifications with a viscosity of SAE 15W40 and meeting ACEA diesel engine oil specifications B296 and E296. Duckham's fundamental philosophy is that quality matters. It makes no sense to spend £15,000 on a car and then put poor quality oil in the sump. That's what motor manufacturers are saying. We agree, and we're sure you will agree too.